Good morning, everyone, and I want to thank you for joining today's webinar session. My name is Blake Wyseth. I'm the Applied Research Lead at the Glacier Farm Media Discovery Farm Langham, and today's webinar presentation is titled The Story Behind the Data. The inspiration for this webinar presentation is really looking at the fact that in today's day and age, we have the tremendous ability to collect enormous amounts of data, either from the hardware or sensors we have installed in the field or the various equipment that we're operating. But that said, we also know that this data, it can be overwhelming at times and really void of meaning unless it's properly interpreted or put within the context of what we're seeing and observing in the field. So with that, I'll be sharing in this webinar presentation, first off, some of the data that we collected in our Field of Excellence project at Discovery Farm, but more importantly, specific applications of that. So the first half of the presentation will focus on how we use that data to inform the management decisions that we made in the field. And then the second half of the presentation will look at the data that we collected throughout the season and at the end of the season to interpret the yield results that we were seeing in the field. So with that, I just have a few quick announcements by way of introduction. I encourage you all to be participating in this webinar and use the chat function on the right side of the screen should you have any questions. And I encourage you to put those in the chat function as they come up, and we'll address them at the end of the webinar. And the other thing I'd like to mention is that we have applied for a 0.5 CEU credit from the Certified Crop Advisors for this webinar session. So for CCAs that are attending, you can feel free to look at the offers tab on the right side of the screen, and the QR code for that CEU credit will be found there. So I would just encourage you to take that in. And finally, we're also excited to be partnering with Metos Canada on this webinar. And at the end of the presentation, I'll be joined by Guy Ash, who's a product expert with Metos Canada. And I'll be asking him a few questions about his experience of farmers and agronomists really leveraging the data that they're able to collect from the Metos hardware and how that's allowing them to make good management decisions in the field. So with that, let's get into the webinar today. By way of introduction, first about the Discovery Farm, this is the name of the entire section of land that's located west of Langham, Saskatchewan. And while there may be a few of you who are not familiar with the Discovery Farm name, I trust you are familiar with the site, as it is the home to Ag in Motion, which is Western Canada's premier outdoor farm expo. And it was at the 2019 Ag in Motion show that we launched this Discovery Farm brand. One of the reasons for that was to speak to the types of activities that we're doing at the site and how we're making use of it really for 365 days out of the year, rather than just the 3 days in July where the Ag in Motion event takes place. So one of the important aspects of that is the applied research program that's conducted over 350 acres at the site. And really, it consists of a number of applied research and demonstration projects along the entire research continuum. Everything from small plot replicated research up to field scale research and demonstration projects that use commercially available equipment and everything in between. So I'll just highlight a couple examples of those types of projects that we do at Discovery Farm. Number one is our Field of Excellence program, and I'll be speaking about this throughout the entire webinar, but by way of brief introduction, this is a program where we're bringing together many different industry partners that represent the entire supply chain, and they're all bringing their expertise in their niche area to this project, and we're working together on a single cohesive protocol and objective. Then we have private sector funded projects like our Yara incubator farm that we're proud to host on the Discovery Farm site. So in this instance, we're partnering with a specific industry partner that wants to do a research project on our site, and we're really just acting as a third-party contract researcher to assist them in doing that project on our site. And then the third category is publicly funded research projects like our water management project that I've spoke to earlier on in our winter webinar series. The entire site is equipped with a state-of-the-art digital farming infrastructure, which we're very fortunate to partner with many different companies like Metos Canada and others to put this infrastructure in place. And practically what that means is we have a number of hardware and sensors installed in the field. We're also pulling other data layers like that available from remote sensing techniques, satellite imagery, and otherwise. And really what that allows us to do is what we're talking about today. It helps us to make these informed management decisions and really interpret the results of what we're seeing in the field. And the final thing I'll say by way of introduction is that knowledge transfer and extension is critically important to everything we do at the Discovery Farm, which is why I'm so happy to be doing this webinar today. But it's about engaging with you folks as our critical stakeholders, be it farmers or agronomists, those working in the industry. We really want to hear from you in terms of your feedback on the projects we're doing. Does it answer the research questions you're interested in? Does it resonate with you? If not, please feel free to let us know that. And we're also looking for future research ideas too. So I would just encourage you to engage with us, and I'll share my contact information at the end of the presentation. I'll just now shut off my camera so that my screen isn't in the way and will block any of the data that's shown on the slides going forward. So now I'll shift gears and talk about the Field of Excellence project. And at the outset, I just want to acknowledge so many industry partners that came together to make this project a reality. And you can see many companies on the bottom of the slide here acknowledged. So thank you very much to all those companies that came together to make this project a reality. To introduce this Field of Excellence, this year, the project was conducted over 180 acres at the Discovery Farm Langham site, and that was split between two crops. So we had 120 acres of CDC Hughes wheat on the north end of the field, and then 60 acres of PV 681 canola on the south end of the field. So you can see those two fields on the satellite image. The colored image that is overlain on top of the satellite image is a SWOT map. And this is a soil mapping tool that is available to us through partnership with CropPro Consulting. And really what this allows us to do is to delineate 10 specific management zones in the field that correlate to the different colors you're seeing on this screen. It's very important that many different data layers come together to make this SWOT map. And it consists of the underlying physical and soil chemical properties. So things like the electrical conductivity, the soil texture, organic matter, nutrient properties, as well as high resolution elevation data that's used to model topography within the field. And importantly, it helps us to understand where water is moving throughout the field. So collectively, between those base soil characteristics and an understanding of water movement, this allows us to develop the SWOT map. And so just to give you some context, the yellow areas within the SWOT map are what's known as Zone 5. These are what you would consider your best performing areas of the field, or what you would expect to be typically your best performing areas of the field. You know, mid-slope locations, good ability to hold water, good organic matter content. And then we have fringe, what I call fringe soils on either end of that Zone 5. So on one end of the spectrum, you have Zone 1 soils. These are the red areas in the field. They're typically upslope locations, perhaps eroded knolls, typically have a sandy soil texture, typically dry. And on the other end of the spectrum, the green soils on the field are zones 8 through 10. And these are typically the wetter areas of the field. They might be saline. They're areas where water collects within the field. So when we have this understanding of the SWOT map, we can use this to choose the locations of the soil moisture probes that we had installed in the field. So we had 12 of these installed, 6 in each of the two crops. And you can see an image of the probe on the right side of the screen with the above ground rain gauge that goes along with it. And so we installed those at the locations of the numbers and letters on this image. And then we also had a complete weather station installed on the site. So collectively, this really served as the base data layer that really informed many of the management practices that we did within the field. Now, as a soil scientist, I'd be remiss if I didn't present any soil information from the site. So thankful for CropPro Consulting for doing some soil sampling in the spring of 2020. And they did a number of analyses, and I presented a couple of them on the screen here. And the results are bulked according to different zones within the field. So just a couple of things to highlight. First, in the top left corner of the screen, organic matter. It's as you might expect, we have this sort of bell curve distribution of organic matter, where again, our zone 5-6 soils have the highest organic matter, and then it sort of tapers off in the fringes. And this is as we would expect for the highest productivity soils having that highest organic matter. In terms of electrical conductivity, we did see a big spike in the upper zone, so zones 7 through 10, and we're just wanting to be mindful of that, and it might help us to interpret, the results that we're seeing in the field later on. And then finally, just looking at the residual nitrate in the spring. So in zones 1 and zones 10, we did see a spike in available nitrate there with reduced nitrate in the middle zone. So I just wanted to set the stage with some of this soil information, and it might be useful when we look at the results that we saw throughout the year. And then finally, soil textural analysis is important. This is the textural analysis reported for 3 zones, zone 1, 5, and 8. And the thing that I want to point out, if you look at zone 1 in the top left corner there, you'll see that there is, as we would expect, a much higher percentage of sand in these soils compared to the other soils. So again, this just confirms what we would expect for a zone 1 soil, sandy in texture. But you can also see variability in texture even within a single field, and a consideration of how that might impact how we manage it and what we see in the field. So with that baseline set, I'll go to highlighting a number of different examples of various precision agriculture applications that we did in this project. And in terms of how this relates to the story behind the data, really it's about picking the right data layer to inform this management practice. So when it comes to seeding, we use the SWOT map for that base data layer. You can see the prescription that was built for our wheat field. So we have our 10 zones on the left, and then we had our wheat seed and 3 fertilizer blends where we did variable rate application of those 4 layers. So wheat seed in pounds per acre, and then 3 fertilizer blends, monoammonium phosphate, urea, and a potassium sulfur blend. And I just want to acknowledge, again, thankful for the partnership of Vaterstad Industries, who provided this seeding equipment for this project. This is a similar prescription that was developed for our canola field. So again, we have our 10 zones on the left and our rates of canola seed, as well as our 3 fertilizer blends. The second example of a VR prescription was when it came to applying our herbicide. And for this, we actually collected a specific data layer to inform that VR prescription. So this was in partnership with CropPro Consulting with their SWOT-CAM technology. And in 2020, it was a pre-commercial version of the technology where Android camera is mounted on the front of a UTV, and this drives on a very high resolution grid pattern throughout the field that you can see on the top left corner of the screen, and literally collects thousands of images that are then fed through a machine learning program that calculates percentage of the crop and weed leaf area. So when you do that and you plot it according to the management zones, some interesting trends emerge. Number one, we see the blue bars for the crop leaf area. We can see that it's relatively consistent across all the management zones. However, for the weed leaf area, we see quite a strong variation from about 4% in zone 1 all the way up to about 17% in zone 10. And so when you have this variation that's correlated very strongly to the management zones, it creates a good situation where you can do that variable rate application. So that's exactly what we did in our canola field here. And this slide shows the logic behind that. On the left side of the screen, you're looking at the weed density map, where the red areas are low weed density and the purple and blue areas are high weed density. So taking that information, the image on the right is the VR prescription that was developed. So simply by varying the volume of water that was applied by your sprayer, sort of the default rate at the low weed density of 10 gallons per acre, you get an application rate of 1.35 liters per acre of Liberty. But by bumping up that volume to 12 gallons per acre, your application rate goes up to 1.62 liters per acre. And so I think this was probably the most satisfying example of precision agriculture from this year, where through a very simple process of just loading that prescription onto your controller, your sprayer, you're able to get better weed control. Now, it's important to note that there are some limitations here. Of course, the capabilities of your sprayer would limit the resolution that you're able to apply that prescription. So in our case, we had 16 sections across the width of the boom that are able to apply unique rates. And also you have to be mindful of the product that you're choosing. So not all products would allow you to vary your rate and stay within label rates. But in this instance, it did work well. So now I'll just pause my presentation briefly and show a video of how we applied this within the field. So just bear with me briefly as I bring up our video. So what you're seeing here is we're going into the area of high weed pressure. If you look at the monitor, that purple area on the screen is our high rate of 1.62 liters per acre. And now as we go to the lower rate of 1.35 liters per acre with the green polygon and scan back to the field, you can see very clearly much less weed pressure in the field. So now I'll just go back to our presentation. And I just wanted to illustrate, that it's just an example of where it's just a great practical example of how you can get that variable rate input application informed by your data. The next example is how we did a top dress UAN application, and the base data layer for this was an available water map that was developed in partnership with CropPro Consulting, where we're taking the base soil moisture measurements from the probes and using that along with the SWOT map to model your available water within the field. So once you have that, then you can understand and predict the crop's demand for nitrogen and build your prescription accordingly. So this is the prescription that was developed for our wheat field, where we had a 0 rate applied in zone 10, and then our rate slid from 5 to 9 gallons per acre across the other zones. And similarly developed for our canola field, where the prescription was shut off in zones 9 and 10, and then we varied it from 5 to 12 gallons per acre in our canola field. The final example of VR application was with fungicide, where we developed an on-off prescription, and the data layer for this is an NDVI image. In the case of our wheat field, it was collected on July 11th. You see that image on the left. The blue areas are areas of high biomass. The brown areas are low biomass due to poor crop growth due to weed pressure or periodic flooding. And so by shutting the prescription off in zone 10, you can see the as applied map on the right side of the screen. The red areas where it was shut off, you end up saving about 6% of your field with not applying that fungicide. And finally, in the canola field, the same process here. By shutting off that prescription, you save nearly 8% of the product being applied in the field. And then it came to crop harvest, and we were thankful to partner with Kloss for providing the harvest equipment for this project. Now, the second half of the presentation is about looking at that data and interpreting it to understand what we observed within the field. On the screen here, this is the type of data output we're used to seeing from many of the instruments installed within the field, where you have an Excel spreadsheet with a number of columns and variables across the top, and then values recorded according to a timestamp. And, this is all good information, but the question is, how do we interpret it? And even a person like myself that's seen a fair amount of spreadsheets in my day, I'll admit it can be quite overwhelming and quite confusing unless you're able to interpret what's going on there. So one of the things I learned early on in my grad studies is to look at the growing season conditions when we're trying to understand what we're seeing in the field. And the first place to start with that, of course, is in rainfall. So I've reported that on this slide here, where we have our growing season rainfall from May to September along the bottom, and then reporting monthly precipitation in millimeters along the y-axis. The orange bars relate to the values that were actually measured from the weather station installed on our site, and then the blue bars represent the 30-year historical average from Environment Canada data. So very clearly, we can see that early on in the growing season, we had above average moisture, from May well into the first half of July. But then from about the middle of July onwards, the taps effectively shut off, and we have below average moisture conditions in the field. What about temperature? This graph here shows the daily max temperature over a 31-day period from July 15th to August 15th. And then I've just drawn a line at that 30 degrees Celsius mark. And so again, you can see on a number of occasions, our temperature has risen above that critical 30 degrees Celsius threshold. So when you combine that impact of temperature and precipitation, I guess it's clear to maybe our conclusion should be, well, of course, that impacted our yield, and that's the answer in terms of what we're seeing in the field. And indeed, it's been long understood that temperature and precipitation does have an impact on canola yield, even going to research from 10 years ago now, where it was determined that those temperatures above that 30 degrees Celsius range at the flowering has a significant impact on limiting canola yield. So is that where we end the story? Is that how we conclude things? That we say, well, we've looked at our precipitation, we've looked at our temperature, and that's the end of the story? And I guess I'm suggesting not. And one of the reasons for this is while we can conclude that temperature and precipitation had an impact across the entire field, how do we deal with variability that we see inside the field? And that's what I've presented in this slide here. So what we're looking at is a detailed results of our canola harvest, where we have our 10 zones along the left, and then we've calculated our gross revenue by looking at the yield and an assumed price of $12 per bushel. In terms of our costs, we have our input costs, which of course vary according to the different prescriptions that we've applied. Our machinery costs remain fixed throughout the entire field, and these are determined by custom machinery rental guide rates published by the government of Saskatchewan. And then you can calculate your total costs and of course your resulting profit. So I've reported the profit for each of the 10 zones as well as a weighted average along the bottom. And as we would expect, in our most profitable zones was zone 4 to 5 in the field. However, we do see significant variability in the field. And so by looking at some of the data coming up, we'll try to tease that out and understand the reason for that variability. So this is a similar slide for our wheat field. Again, we've just reported our yield and revenue according to the zones, and then understanding our costs, we determine our profit. And similarly in our wheat, again, our highest productivity and profitable zones is that zone 5. We were still able to maintain decent profitability in the fringe zones. However, there is, I would suggest there's a different reason why we see a drop in profitability in, as an example, the zone 1 soils compared to the zone 8 or 9 soils. And I'll go into that here shortly. I think the first place that we can understand and really tease into the variability within the field is to look at the interaction between precipitation and how that impacts soil moisture within the field. And that's what I've shown in this slide here. I will admit there's a lot of information going on this slide, so bear with me as I break it down for you. So first off, we're looking at the precipitation, and I've reported the precipitation over about a 150-day period, with day 0 being May 1st and day 150 being the end of September, and showing precipitation in millimeters. So very clearly you can see where these big precipitation events are. As an example, around day 20 we had about 40 mils in an event. Right before day 40 we had another big event around 55 mils or so. The second layer is when you overlay that with the soil moisture data that was collected at sort of the two extremes in the field. So the zone 1 locations in green, as you can see, remember these are what we would expect to be our dry areas in the field, and zone 8 in blue, is what we would expect to be the wet areas. And these measurements were from the 10 centimeter depth in both of the locations. And so what you can clearly see, of course, is number one, we see the impact of the precipitation event in terms of what's measured in the soil moisture. So at that day 40 event, you can see the big spike in precipitation. And then a few days afterwards, the resulting spike in the soil moisture that's measured. And we're reporting volumetric soil moisture content in percentage along the y-axis. The other thing to note is just the difference between the two probes. So again, the zone 1 soil much drier than the zone 8 soils. Now let's look at those same probes, but look at a deeper measurement. So now looking at the 120 centimeter depth, in this case, we see that the moisture is held constant throughout the entire growing season. There is, of course, still a difference where the zone 8 soils, that blue line, is wetter than those zone 1 soils, but that measurement is held constant throughout the entire growing season. So now when we bring that data all back together, a couple observations jump out to me. Number one, we do see substantial variability in our soil moisture early on in the growing season. And that would be expected. You know, we're getting those rainfall events, and of course it's going to impact the two soils differently. As you can see, the gaps between those two lines. However, later on in the growing season, it's interesting that those two lines essentially merge. So where, you know, from about middle of July onwards, the soil moisture at both extremes within the field is essentially the same. And so by extension, we can assume that throughout the entire field, the surface soil moisture at that 10 centimeter depth is approximately constant. However, we do see a difference in the moisture at depth throughout the entire growing season. So again, whereby that blue line at a volumetric soil moisture content of about 60%, we can assume that this is saturation. And my interpretation of that is that we've hit the water table at that zone 8 location. In contrast, though, at the zone 1 location, we're still seeing good moisture, you know, about 40% volumetric soil moisture content. So not at saturation, but it presumably is, you know, supplying some moisture to the crop throughout the growing season. However, I'm making the assumption, and also later, that zone 1 location, even though there was moisture at depth, it was not enough to continue to supply moisture to the crop to put on those bushels at the end of the growing season. Another way of looking at this is to look at the interaction between soil moisture at different depths at the same location and by zone. And so how I've done that is to just look at a snapshot in soil moisture on June 22nd and looking at how that impacts soil moisture at different depths and different locations in the field. So on this, I'm reporting measurements taken from a single probe installed at zone 1 in the blue line, zone 5 in the orange line, and zone 8 in the gray line. And then we're reporting volumetric soil moisture along the entire depth of the probe. So we're making measurements in 10 centimeter increments from the surface down to 120 centimeters. So what jumps out to me, of course, is we see again, our zone 1 soils are dry, where maybe you can say we're averaging about 30% soil moisture across the entire soil profile. On the other end of the spectrum, our zone 8 soils are much wetter. And even at a depth of about 20 centimeters, we're already at about 50% volumetric soil moisture and hit saturation even at about a depth of 40 centimeters. And then for the zone 5 soils, we see that they're a little bit drier than zone 8, of course, but still good moisture even at a depth of about 30 centimeters. And by the time it hits 70 centimeters, essentially that moisture profile is following very closely with what we're seeing at the zone 8 locations. The final data layer that can help us understand what we're seeing in the field is the harvest results that were the post-harvest soil test results, which is what I'm showing on this screen here. So I've just reported the results from a few zones, 1, 5, and 8, and we've shown our yield data again, along with the moisture content of the grain, and then a few select soil parameters that were measured from the 0 to 15 centimeter depth. A couple of things jump out to me is, number one, at our zone 1 location, we did see some residual nutrients in terms of nitrate and phosphate compared to the other soils. And secondly, at that zone 8 location, as we saw earlier, there is an increased electrical conductivity value. And so we're expecting that the salinity would have an impact on our yield at that location. So now to bring this together and go again to our canola results, and let's see if we can't tease out maybe some of the reasons why we're seeing differences in yield response across the field. So again, just for reminder, our highest Net profitability was in the zone 4 and 5 locations in the field. And then in terms of looking at the contrast in moisture availability, in our zone 1 location, our yield was limited, I think, because of that lack of available moisture that we saw in the second half of the growing season. And I think that's confirmed by the soil moisture results, even at depth where moisture was limited, as well as our soil test results where we saw residual nutrients left over. It seems like the crop was just not able to access those nutrients. Now, on the other end of the spectrum, in our upper zone soils, 8 through 10, we were still able to maintain a respectable profit for these soils. There's a couple of reasons. Number one, you'll notice that our input costs were drastically reduced in these upper zones because we're making use of the residual nutrients that we typically see in these soils. And in our case, it's residual sulfate, residual nitrate. So we were able to dial back our inputs at the time of seeding and realize some of those savings. But also there's an impact of the electrical conductivity and perhaps salinity limiting some of our yield potential in these upper zone soils. So now, in summary, from this year, we saw that soil moisture did vary significantly within the field at a single location over the growing season and at depth. We also saw that soil moisture does cause a differential impact on crop yield. And finally, we saw that moisture at depth could have an ability to buffer against some of those environmental stresses. So again, in our example here, my suggestion looking at the data is that our zone 5 soils compared to the zone 1 and zone 8, at the surface, the moisture content was approximately the same. If you remember back to that one graph where those lines were essentially merged. However, at that zone 5 soil, I'm suggesting that it was able to access some of that moisture at depth that really helped to drive the crop growth and put on the increased yield. Now, of course, we have to be cautious and not to oversimplify things. Certainly, there's other variables at play, like perhaps the increased organic matter at those zone 5 soils and the ability that has to really hold on to moisture as well. So certainly that is a consideration. But I guess my point is that I think it's important for us to be considering that moisture at depth in terms of explaining some of the varied response in terms of yield throughout the field. So finally, the slide that I've called "So What?" I mean, at the end of the day, what does all this data mean? Unless we're able to use it to make management decisions or maybe refine the way that we're farming, it's without meaning. So some of the questions that come to my mind from looking at this data are, how do we best leverage or manage the moisture variability we're seeing in the field? How do we keep water in those upslope areas to buffer against drying out at the second half of the season? Or how do we manage periodic flooding in our depressions? How do we also manage yield limiting salinity? Is there a place for forages or intercropping with salt-tolerant varieties or crops? And this is one of the things we're exploring in our salinity project at the Discovery Farm, where we're testing out different combinations of perennial forages to manage salinity. And how can end-of-season moisture and other data be used for spring fertility planning? So with that, it concludes my portion of the presentation. I'll leave my contact information up here very briefly, but also again, just reach out to you folks and ask you to please connect with us. And if you want to get in touch with me, here's the way you can best do that. And I'd love to hear from you for your feedback on our projects or for future presentation ideas. And now I will stop my presentation and go to the next portion of the presentation, where we'll be hearing from Guy Ash, who is, again, the product expert with Metos Canada. I have a few questions prepared for Guy, and really what this is looking at is I'm wanting to hear his expertise and hear how he's heard his agronomists and growers are, again, making use of some of the data that's available to them from hardware at Metos Canada. So Guy, thanks for joining me today. My first question for you is, this year at Discovery Farm, we saw how soil moisture can vary so drastically throughout the field. And one of the things I know that Metos is excited about is their Mobi Lab that's been recently released. as a tool that can assess that variability in soil nitrogen and plant nutrients in a quick and a cost-effective manner. So I'm wondering if you can share for us, how have you really seen growers or agronomists really making use of this, and especially maybe in combination with other tools like soil moisture to impact the way that they're managing their fields?
Okay, thanks, Mike. You hear me okay?
Yeah, I do.
Good. That was a great presentation and study on the variability across a field and how much it does change, and the need to really monitor and keep track of everything and tune your management system. So, today I'm talking a little bit about in-field IoT devices and how they can be used on the farm. And really, it's not one solution. It's a nested approach. And you touched on all that today, where if I want to study soil moisture, I've got to have stations and probes in the ground to do that in various areas. I need to use satellite data. I need nutrition management information on the fly. There's a lot of things that need to be tracked. So it's a whole host of solutions, including things for insect detection, standardized weather, even an animal welfare. So in our toolbox at Pestle Instruments and Metos Canada, we have a whole host of different devices that we can implement in what we call this nested approach to Internet of Things for agriculture today. And it's growing, very much growing each day in terms of what we can do. So it's a set of actionable tools that provide the intelligence to somebody on the ground. The key is the boots on the ground, such as you, of course, on your Discovery farm, that are making these decisions on that farm or advising a farmer. So it's absolute key, boots on the ground through actionable tools and whatever it is in terms of data collection. Could be insects, weather, soil moisture, nutrient management. They're all part of the picture of what we use. So the value proposition for soil moisture monitoring is extreme, because you can place these probes today in areas that you want within the field in various soil types like you're doing. You can monitor soil moisture levels at various sensors, which we see here on the app. So we can actually know at each sensor what's going on, and if we're at the refill point or field capacity based on that soil type. We can monitor, most importantly, as you were defining, the root zone soil moisture. We have a whole profile, but it's the rooting zone that's absolutely critical for moisture, where the roots are tapping water, and apply that to the developmental stage of development, and knowing how much is there, right? How many millimeters of water or inches of water in that profile equates to a yield potential, whether it's in irrigated or dryland situation. So all that leads to very effective management schemes that you can apply in a nested approach. The traditional way was really to look at our crop and how much water it was using over time, and based on the stage, whether you're in vegetative or reproductive, where the root zone was, and come out with some estimate of how much water I should apply to that particular field if I was irrigating it. Well, today with these probes, you can certainly have a very, very detailed look of what's happening in absolutely every profile of the probe. So every 10 centimeters down, in this case, to 90 centimeters. And we can see a stair-stepping approach, which is the day-night evapotranspiration, where the roots are withdrawing water. And you can see up here kind of a flatline approach where the roots aren't tapping into water. You can also see how much water was added, where the graph is picked up, and how far that water made it down into the profile. So there's a lot of data that you can glean from it. But the key is really it needs to be put into a tool set that makes it easy for somebody to understand. So today it's about holistically combining a lot of different sets of information. So we have satellite imagery that's available for the location, and we're looking at the Discovery farm here. Why is there differences in leaf area index or NDVI in that field? Is it because there's a difference in soil moisture within that field, as we saw, or is it something that has to deal with nutrition in the field? So it's a combination of IoT devices that you can be used to figure out what the problem is in productive and non-productive areas. So whether it's the vegetative state because of a lack of moisture in the sum of moisture in the rooting zone, or I could go in with what we call a mobile lab device, which is the ability to do your own soil chemistry or plant sap analysis right at your own farm and have results within a couple hours of that particular location. So now you can go into a field and take a whole number of samples, not one, but a whole host of samples, come back and assess very quickly what I have in terms of nutrients in my field. And maybe these spots that you see in the field that are poor versus high is because of a nutrient problem, along with a moisture problem. So that's how today I see the combination occurring: geospatial data being integrated, the point data from probes, the satellite imagery, soils data, and even now the collection of samples that you can do within a field.
Thanks, Guy. So the other thing that I'm really excited about is, with ready access to localized meteorological data and the computing power to really process that data, we're seeing predictive modeling tools emerge for insect and disease infestations. They're already being used across the world, particularly in high value crops, but also field crops. And so I'm just wondering, Guy, what are some of the applications of this technology on the horizon for broadacre prairie crops that really excite you?
Yeah, it's a good question. There's a lot of things that you can do once you have data in the field and put it through a actionable tool that gives you kind of a stoplight system of what's going on. One is obviously disease management. So things like, in canola, sclerotinia, blackleg, very big issue. So we can use weather stations to create models that will predict the apothecia development, even the spore release and the spore infection. So these models get very specific and broken down, which really is about the timing of fungicide applications based on not only the disease risk pressure, but also the growth stage. So I call that the synchrony of the crop to the actual problem. What you're doing then is really trying to preserve your yield and quality based on well-timed fungicide applications. So today in software, it's all about modeling the disease triangle: the host, the pathogen, and the environment. Typically is the environment that tips the scale in favor of the pathogen and the natural defenses of a host plant, where you need to use a fungicide to help protect that particular problem. So it's really looking at what are the right environmental conditions that lead to this particular disease. And there's one thing a in-field device can do is very accurately track what's happening in terms of the weather for the biology of that particular pathogen. In this case, it's being sclerotinia that we're talking about. So in our software, we can have the ability based on very local conditions. So we're looking at high leaf wetness periods, rainfall, high humidity, nice temperatures, and we can actually see when the apothecia begin to develop, when a sporulation event takes place, which is a binary response, on or off, the spores are released, and then whether you're into a aposoria or hydrolytic infection in terms of development. So that's the level of breakdown, and that occurs because you have a very sophisticated model that's been developed over time and applied in numerous countries of the world for application. And it's based on the biological process of that particular disease. So you can actually see a difference. I wanted to do a little study to show the importance of localized data. So here at the Discovery Farm, you can see a layout of all the devices. You can see the weather station up at the office and the weather station down here at the corner, which is maybe a mile or so apart in the actual field. And you can clearly see the model sensitivity to the actual data. So here we're looking at the main office, and you can see the weather that occurs at the same period of time. Here we actually have a sporulation event, apothecia, and we actually get into a hydrolytic infection. Here we don't ever get into any major event of infection. We do have the sporulation, we do have the apothecia development, but it's a shorter period of time. So the microclimate that's occurring in that crop is picked up by the weather station. The model is then showing you its sensitivity to showing the impact of that localized data in that field. So that's an example, I think, of other IoT applications in disease forecasting and prediction that will be used widespread. And this can apply in cereals, in pulse crops, all kinds of things today.
Thanks, Guy. And my final question for you is, recognizing that IoT is a stacked industry. However, we know that rural connectivity can be an issue in certain areas of the prairies, preventing the IoT hardware from properly transmitting the data. So my question for you is, how has Metos addressed this issue in terms of the hardware options they offer farmers?
Yeah, this is probably the most important question, as you described. It's a stacked industry. There's numerous pieces that need to come together to make this work. And telecommunications and communications is, one of the most important. So you have a device that has a SIM card. It's got a modem. It has a, data logger in it. It has sensors attached to it. All that has to work. If one piece doesn't work, you don't have data. And one of the biggest things is to make sure we have connectivity to collect the data wherever it is. So today there's a revolution going on in what I call telecommunications. Today we're all used to using LTE on our smartphone. And of course, many of the devices we're talking about here at the bottom use LTE or will use 4G or 3G. The modems are backhaul compliant. So if you don't have LTE, they'll use 4G or 3G. And even today, the 5G push for autonomous vehicles and much higher data volume. But these are, real high capacity type connectivity. So things like cameras will always be LTE or beyond because of the amount of data. For what we're doing in a farm, like soil moisture collection or weather data, I don't need that speed. I can move over to these other options that are now being released, and you'll hear them like NB-IoT or Cat-M1 or LTE-M. Those are all smaller packets of data designed for, and LoRa is another example of that. So LoRa is another what we would call the wide area low powered network that can collect data. What's the difference here? Small amounts of data collected, less cost. So that's less costly in terms of the data collection, and the distance covered on some of these can be further as well. So all these devices today in terms of PESTLE have an awful lot of wide range of capability of data logging. So we provide things in LTE, we provide things in LoRa, we provide things in NB-IoT because it varies all over the world. Some countries like France will be 99% LoRa compliant. In Canada and the US, it's a lot of Cat-M, NB-IoT that's being deployed. So we can implement these different collection modems, telecommunication ways in our hardware to be able to provide you data collection on farm and in the field. What we can't guarantee, of course, is the connectivity for the tower. The tower is, where is the tower, and the connection to that tower is still critically important, where we still need to improve our networks across Western Canada and Eastern Canada for that. So connectivity is the key for IoT success moving forward. Thank you.
Perfect. Thanks so much, Guy. So with that, we'll turn to our question and answer portion of the session. And I'm really encouraged to see there's so many great questions coming up on the screen here. But before we get to those, I'll just switch back and share my contact information from my slide deck in case anyone, again, wants to reach out to us at the end of the presentation.
I guess I was going to make one comment, Blake, if I can, about the special offer. So if you
go ahead.
Offer, Metos Canada is offering 10% off for people on the webinar. 10% off any subscription package, and the offer ends March 1st. So if you go to Metos Canada, you can get 10% off any subscription package that's listed on the Metos Canada website.
Perfect.
Thank you. Thank you, Blake.
Thanks very much, Guy. So yeah, I'm just continuing to bring the slides up here. But again, I just want to thank you all for putting your questions in the chat. And we'll try to get to as many as we can here in the next 10 minutes. But if not, I'm sure Guy and myself are available to connect with you again, after the presentation. So the first question, and I'm not sure in no particular order, just the order that I see on the screen, on my screen, is a question from Les Henry. And I'm thankful that Les joined the session here today. Les asked about, how is the yield data collected, with a 40-foot combine header? And great question, Les. So really, this is another instance where it boils down to the fact that data on its own really is useless unless it's properly, interpreted. So in the instance of our equipment setup we had here in partnership with Kloss, the capabilities on their machine, they're able to collect the yield data, of course, but then geo-reference it to GPS location. And then we took that data and sent it in partnership with our partners at Crop Pro Consulting to do some of the back-end processing of that data. So I guess there's a few things at play. I know they have a lot of experience in really interpreting and processing that data appropriately. There is no doubt an instance where you're crossing through two management zones, and you're only getting one yield result across two zones. So I'm not exactly sure how they do that back end processing. But additionally, I also collected square meter samples within each of the zones and did my own harvest on those for high resolution data to sort of confirm and validate the yield data we were seeing off the combine. So great question there. Now I'll just go back, scroll down to the bottom here. Just wanting to make sure that I got all the questions. So Norman asked a question about, gathering the data with a UAV, and I think Derek Rude on the call, on the chat function answered that. So thanks very much to Derek for that one. Michael asks, do you have piezometric data to back up what the moisture probes are providing? And also, do you grab samples to verify the volumetric moisture contents? So Michael, that's a great question. And I guess currently I would say that no, we didn't have piezometric data, piezometric monitoring wells currently installed at the Discovery Farm. That is definitely something we want to look towards. And I think really it speaks to, as we're growing the Discovery Farm, we'll definitely be looking to kind of add that information to validate what we're seeing. The other thing too, I think I just want to, make clear about the types of project we're doing, that as a demonstration project, I think it's important that we're really framing this within the context of, this is what we're seeing at this location in this season. So not necessarily, these results are going to translate perfectly to all locations, across Canada as well. But importantly, I think what I would like to do is encourage you folks on the call to take this back and do your own validation and further research to kind of confirm what we're seeing in the field. So great question there. Michael asks, another question, how does the dollar per acre return from a variable rate fertilizer compare to dollar per acre on conventional blanket rate fertilization? So that's another great question. The way that we kind of went about sort of answering that is by reporting the data, broken down per zones, and then also with sort of this weighted average number. And I guess just to illustrate that, there's certainly variability within the field where certain areas are going to be more profitable than others, which of course we would expect. But yeah, to your question on, we did not have a direct comparison on, a variable rate application compared to a conventional blanket rate application. And one of the reasons for this is I think it's a really interesting question, but it's just, in my mind, it'd be difficult to set up that type of a study. So I'm really curious if maybe others have experience doing these types of projects, but again, to really have sort of an apple to apple comparison of where you're doing the same this comparison on, same baseline soil conditions to really tease out that response. It would be a really neat study, but we didn't have that direct comparison in this project year. Going up the list of questions, Norm asks again about machinery costs and how they're all the same across the zones. And that's a good point in terms of, the fungicide or the N application. And yeah, definitely point taken. That's definitely something I'll have to consider in further refining the economic analysis. But no, I didn't account for that difference in those zone 10s as an example, where we're shutting off the fungicide application. I guess I was more so treating, the variable rate fertility. Of course, that difference is reflected because we know, the exact fertilizer costs we're applying in each zone, which is the main reason for the difference. And then, based on the number of passes of herbicide application and those sorts of things. But no, that's a good point for further refining the results here. I'll maybe give Guy a chance to answer some of the questions that we're seeing here too. And I noticed one especially, I think, was meant for Guy. It was, so there was one question, especially, I guess, and I think you may have touched on it, Guy, but if you can just address it again. Jean-Claude asks, some remote areas may depend on centralized internet connectivity at the farmyard. Is there a radio link option in lieu of cellular link? Not all rural areas have good cellular data options. Wondering if you can just reiterate that one.
Yeah, I kind of went over that stuff quick because I was moving through it, but I think that's where LoRa comes in. And LoRa allows an individual to actually put a gateway up, and that gateway then backhauls through some connectivity. It has to be through internet or LTE, but that gateway would allow a whole number of devices to communicate to it. So the higher up the gateway is at the farm, the further you can reach. So it's essentially like a radio link to devices. So LoRa is a way for an individual farmer to have a gateway, collect data from numerous devices out there, and backhaul it back through some connectivity, LTE, internet, to the server, and you then have access to your data. So LoRa is a good, powerful way. And in Saskatchewan, there's quite a bit of LoRa development going on. And if you need more information on that, you can certainly contact Blake or myself, and we'll answer more detail.
Perfect. And then I guess recognizing that our time is quickly coming to a close here, just want to thank everyone for joining today's session. Really appreciate all the interaction, all the questions on the chat. My contact information is on the screen here. Please feel free to reach out and contact us. If anyone is interested in getting in touch with Guy, we can definitely connect you with him as well. So with that, I just want to thank you all again for joining this webinar session, and wish you all a great rest of the day and a good growing season coming up. Thanks very much, everyone.